All right, so 214 is called log function context and modeling and data modeling. So context means word problems, real world usually application. Data modeling means we're going to figure out how to find the regression using the calculator, now log. Okay, so that's kind of what these things keep coming back to us as. So first, as a reminder, we already did this, but remember that log functions have independent input values that increase proportionally or multiplicatively, while dependent or output values increase at a constant rate or additively. There's a lot of vocab in there that you have to pay attention to, okay? Our x values have to be called independent values or input values. Those mean the same thing as literally saying the x values. But your word problems are not going to say x values. They're going to say those kinds of things. Independent, input, all of that means what you're plugging in. And then they increase proportionally or multiplicatively. Those two things mean the same thing. If you look at the x values here, or the input values, they are increasing multiplicatively, specifically being multiplied by what this time? Times 4 each of these times. And then the dependent, so again, important vocab, dependent or output values, this is your f of x, this is your y. Those increase at a constant rate or additively. So you can say constant rate or you can say additively. If you are describing the context, obviously you can use either of those things. If they are describing it, if it's like multiple choice and you'll see it written in words, you have to pay attention that those things mean the same thing. They will either use independent or input, or they will use dependent or output, or specific to that data. So if we are plugging in something and it gives me that whatever that term is, right? If it's the number of people or any kind of input, then you're going to be specific on those things. And then the output, same thing. It could use either output dependent or it could use whatever the specific thing is. So this would be your f of x or your y or your output. And notice those are increasing. Now they're increasing at a constant rate, but it's not 1, right? From 5 to 7, 7 to 9, 9 to 11, and 11 to 13. What's it increasing by? 2. As long as it's constant each time, it doesn't have to be 1. And then the bottom says the amount the proportional value increases of the input values would be the base of the log function. So because we're multiplying by 4 this time, our log base would be 4. If we were multiplying by a half, well, not a half. If we were multiplying by 3, then our log base would be 3. You could be multiplying by a half, and then your log base would be a half, but something like that. All right, so example 1 says, as the school day goes on, Mrs. Christweiser's room gets warmer. As the number of students increases, so does the temperature. And then it gives you the data. So the number of students increases from 6 to 36 to 72 to 144. And the temperature increases 62, 64, 66, and 68. So obviously it could say, is this log? And we would say yes. And why? How do you justify its log data?
The input is increasing multiply.
Good.
The output is increasing additively.
Good. So the input increasing multiplicatively, input increasing additively, okay? This says what's a regression equation to model the situation. So we're actually going to find it using our graphing utilities. We're going to put in the data just like we've been doing, okay? And, well, I'll get to it when we look at it. But you'll see what the stat plot looks like this time. It's a little different. Not the stat plot, but the options for stat plot. So open up your stat plot. Type in that information. All right, so I've entered, you can't see it. Okay, I entered my data into the stat plot, okay? Now when we go back to stat and we go to calc, you can look through this list and you will not see log. You will see logistic, which is not the same thing. but you should also see ln. So it's not going to find you a log with a specific base. It will find you the ln equation. So I'm going to hit ln, reg. I'm going to store it because we're going to answer questions based on it. Second, or alpha, trace, y1, and I'm going to calculate. And there's my regression model. Y equals the A, which is 58.314, plus B, which is 1.829 ln of x. And that's how I'll write my log function, or f of x equals same thing. If it gave me something like the students were S and the temperature was T, this would be rewritten, right, as F of S or T of S if it told you that the model was T. You got to just make sure you're paying attention to specifics like that. Questions so far? Okay, then B says, what's the temperature if there are 45 students? So what do I do with 45? Students is what? The X or the Y? The X. So go Y1 and 45. And I get 65.277. Can a temperature have a decimal? Sure. Okay, so this would be in degrees. I would keep it if it wanted the unit. And then C says, how many students are there when the temperature reaches 73 degrees? How do I find that? Good. So I'm going to do Y. I'm going to add 73 here. I'm going to graph it. I don't see it. Why? My window, right? Look, the vertical shift is 58, which means it's way up, okay? So yesterday, oh, let me see if it works. Yesterday we discovered something else. Zoom 0. Sometimes it works and sometimes it doesn't. It's supposed to take you to the intersection. It didn't work. Okay, so we have to adjust the window. So I know that my Y is good. My Y min, I want to actually see over it. So I'm going to leave it as it is. It could have been 50, whatever it is, and then 75, but my X max is not big enough. So let's do 100 and let's see what happens. Not even close. Oh, okay. So we're going to keep going.
They're like stacked on top of each other.
So we're going to talk about a different way to solve this for a situation like this. Oh, not even. Okay.
But it's like 3,000.
It's like 3,000. I actually already know this answer because I already did this, but I'm just going to pretend like we don't, because what would happen if I didn't? I would have to keep going.
You need to see the intersection.
In order for the calc to find your intersection, it has to be on the range. Yep. All right, so now it's there. Okay, so I'm going to do second, trace, and I'm going to find the intersection. You could have kept zooming out. Like I could have hit zoom out, zoom out, zoom out as many times until it crosses, which now it crosses. 3,070.49 is what I got. 3,070.491 technically, okay? So we're going to talk about an approach to do with this in a minute, but think about that answer. Can you have 0.491 of a person? No. So if I round down, I have 3,070. Has my temperature hit 73 yet? No. So even though by rounding rules this would round down, we have to round up because it hasn't happened yet. So if you want it to reach 70, then there had to have been 3,071 students in the room. And then Mrs. Chris Weiser would quit her job because that's too many kids in one space. Questions on the graphing approach to this, because we're going to do it a different way.
Why did you round up?
Because if it's 3, so technically it's a person, we have to keep it a whole number. We would have normally rounded down, but it's not at 73 yet. It might be at 79 or 72 point something, but the question says when, like how many are there in the room when it reaches 70 degrees? So it has to reach 70, and that means you have to push another person in, okay? So if it's an object in which you can't have part of it, then we have to round up, because it's not gonna happen if we round down. All right, so now let's think about what happens if my graph was like it was and we didn't keep trying, right? How else could we solve this algebraically? Just plug in your 73 to your y. So 73 would equal 58.314 plus 1.829 ln of x. How do we solve this? Subtract the 58.314. So 73 minus 58.314, and I get 14.686 equals 1.829 ln of x. Then what? Divide by 1.829. And I get ln of x equals 8.0295, so on and so forth. And I don't want to round that number, right? The more we round, the less accurate it becomes. Then what? Good. This is og base e. So e comes over and picks that exponent up. So if we do e to the answer, which is above your little negative, it will pick up that last answer, and I'd get 3,070.28. And again, I can't have 0.28 of a person, so this gets bumped up to 3071. So if you're quick with your graph, it's easy to see it. Obviously, you can use your graph. If it's so hard to see it because it's so big it's not on your screen and you keep zooming out and you can't find it, then you can do this algebraically. So anything that has a log in it that you're setting equal to a value, so if you have a y for it, then you can solve that way. Remember, if it was like on, these are kind of one of those questions where it said solve it algebraically, show your steps. If this was an FRQ, I would have had that work. And if it said use the calculator, justify your steps, you would have had to say for y, I literally would have had to go through the whole regression process. I entered in the stat plot, I found the regression of ln, I stored it in y1, then I in y2 stored 73, then I graphed it, and then I found the intersection. So you'd have to literally justify your steps if it said, if you use the calculator, explain your process. It might be faster to do it algebraically at that point. Questions? All right. Example 2 says the college admission rate for a university can be modeled by the function a, given by a of x equals 45.56 plus 12.772 ln of x. A of x gives the number of admissions in thousands, which is obviously important, for x months after the first day of admission. A says how many students would be admitted after the 4th month. What do I do with that? Just make that my x, right? The 4 would be the 4th month. The month is your x. So I'm going to do 45.56 plus 12.72 ln of 4. And I get 63.194, but it's in thousands. So you either have to say thousand, or you have to say, hello, there, or you have to move your decimal place. So it'd be 63,194. And you can keep your decimal there. No, because it's people, it wouldn't matter. Right? How many students? It would be that. If you move it, make sure you add on the rounding. So it would be 63, actually this one I think they'll usually keep rounded, or we'll say round to the nearest whole number, something like that. So you'll be fine. It's the ones that are like this, at what month, that's when you always have to bump up. So the ones where you're given the Y. So then C or B says, during what month does the admission count reach 73,000 students? So what does 73,000 represent? What variable? It's your y or your a of x, but this is in thousands, right? And my equation is in thousands. So what do I have to do? Can I keep that as 73,000? Can I write it like this? And then the rest of that equation? No. If that says 73,000, but my equation is in thousands, I have to make this 73. Does that make sense? So be careful with your units. All right, so now we're going to do both ways. We're going to solve it algebraically. I'm going to subtract the 45.56. So 73 minus 45.56. I get 27.44 equals 1272 ln of x. Divide both sides by 1272. And then I get like 2.1572, so on. And that equals ln of x, which means this is really log base e. And e is going to come and pick that up. To keep it exact, I'm going to keep the answer as my exponent. So second e, second answer. And I get 8.64717, whatever. Okay. And this is what unit? Months. Is months in thousands? Like, would I move that decimal? No. But it says during what month? It can't be 8.6, right? So what month does it hit 73,000? At 8, it's under 73,000, right? Which means 9. So no matter what the rounding is, it has to be after that if it's a whole number. So in my opinion, these kinds of questions should be relatively easy. The challenge is going to be, you're not going to get an A and a B all the time. So you kind of have to figure out if it's only asking one of those, what is that? Is that my input value? Am I just plugging it in? Or is it my output value where I have to set it equal to it? Because you're going to get both kinds of questions. Questions on this one? All right. This is actually a slide taken from, I think it's 2.5. But we've done these before, so just as a quick refresher, I didn't want to have to type this all out again. Increase and decrease we won't typically see in these kinds of word problems, but you are going to see half-life, double-life, continuous. So remember, if it says something has a half-life of, and then it gives you whatever that time frame is, that my equation looks like this. So if it says it starts at 100 whatevers, and the half-life is every 5 years, then this would be T over 5. Or 5 months, or 5 whatever, okay? If it said it doubles, so on your double life, the base just changes. It says it starts at 100, and it doubles every 5 years. It's still the same thing. The only thing that changes is the base on that exponential function. All right, and then that last part is continuous. So if something increases continuously, it could be money, it could be bacteria, it could be whatever it is, then we use that PERT formula, okay? So if it said it started with whatever, again, 100 of the things, and it increases continuously, it would be E to the R. So if it if it's at a rate of like let's say it's a rate of 25%, it would be a rate of 0.25 times T. All right, so again, those 3 formulas you have to know, and any of them could show up in this word problem. So going into example 3, it says the number of bacteria growing in a petri dish doubles every day. There were initially 800 bacteria. A, write a function f that gives time in days as an output value, and then a certain number B for the population of bacteria as an input value. So think about why this is weird. Our initial, this would be, it says it doubles, right? So this is a double life. We normally have it equal to the amount of bacteria, right? So the number of bacteria equals the 800 times 2, and it says it doubles every day. So if this is in terms of days, then it's just T over 1, or just T. If it said it doubled every 10 days, it would be T over 10, okay? This question says, write a function f that gives time in days as the output value. So where does the T have to go? God bless you. Where the Y is. I have to now solve this equation for time. Does that make sense? So T time is output. Output goes on the left, right? Where the y equals normally is your output. So I have to solve this equation for T. So I can make this f of x for now, or I could make that y. It doesn't matter. If I had y equals 800 times 2 to the t, how am I going to solve for t? Divide by 800. I heard find the log, which we'll get to both because you could start both ways. And then 2 to the t. Sure. And then you're going to log both sides, and specifically log base 2 because I want to get rid of the base on that t. So I get log base 2 of y over 800 equals log base 2 of 2 to the t, cancels to give me just t. So time equals log base 2 of y over 800 would be the equation solved for t. And actually it says the number of bacteria is b. So we're going to change the y to b. Oops. And you could have done that from the beginning. Like you could have made it b from the beginning. But that's what you're looking for. So you have to, again, know your vocab enough to know that output means where the y goes, and that's the one I have to isolate. Now somebody at the beginning said, let's do b this time, b equals 800 2 to the t. Said to find the log first. So if I log both sides of this equation, this is where it gets sticky. I would have to log b equals, and I would log 800 plus log 2 to the t. So like, let's say this was a base of 2. Then I would be subtracting the log base 2 of 800, and I'd actually have to find that value if I could, and then log base 2 of 2 would be the t. So these are equivalent, like you could use both of them because you could do it in either way, but I think the first way is easier. Get rid of the coefficient on the log first, on the exponential function first, and then move it. Yeah.
Wait, it's like, what is log base of 1?
There is no such thing. Because there would be no growth there. It would always be whatever. It could be any, right? It would always be 1 because you can't raise. The answer would always be 1. Like even log base 1 of 1, I don't think technically you're supposed to be able to do. Like the base can't be 1. Questions so far? Okay, then B says, how many days does it take for the population to reach 20,000? So 20,000 represents which variable here? B. So I can either, and you could use this either way, I could go here or I could do it here. The benefit of doing it in here is that t is already isolated. So if I do that, I get t equals log base 2 of 20,000 over 800. And then I cross through my zeros. Question that when I simplified this was doable. That could be on the non-calculator portion. Does that make sense? We didn't need the calculator up here, right? And if it gave you something here that was, that you could raise 2 to, let's say, then it could actually be done without a calculator. This time we had the calculator, so it doesn't matter. Okay, and again, how many days does it take for it to reach the population? If it doesn't specifically state, like, a day could be a decimal. But if it says at what day does it hit that, now it would be 5. So you have to be really careful on the wording. Yeah. So this wording, no. With this wording, the answer would be 4.644. If it says on what day does it reach 20,000, that answer is the 5th day. Does that make sense? And if it's a person, you can't have a percentage. A decimal part. Not a lot, but yeah. Yeah, you have to be really specific because I feel like that's one of those things that they would be specific on. Questions on that one? All right, Example 4 says a weed grows continuously in a garden. The weed is initially 6 inches tall. The exponential model is h equals 6 times e to the t over 4. So it actually gives you the model already. Write a function g that gives the time in weeks as an output value and a certain number h for the height of the weed as an input value. So what do I have to do here? I have to solve for t. So I need h equals 6 times e to the t over 4. For step 1? Divide by 6. So h over 6 equals e to the t over 4. Then ln both sides because ln will cancel with e. ln of h over 6 equals ln of e cancels t over 4. Then multiply by 4. So t equals 4 ln h over 6. And it actually says function g. So I would rewrite that as g of h equals 4 ln h over 6. But it's beneficial for us to remember that this is time for something like the second part of this question. B says find the number of weeks it takes for the weed to reach a height of 20 inches. So I'm just plugging 20 into my h. So 4 times ln of 20 over 6, and then your calculator can do that whole thing. 4 ln 20 divided by 6. And I get 4.816 weeks. So we would leave it rounded. If it had said, in what week would it reach 20 inches, then my answer would be what? Good, in the 5th week. Questions? All right, if you want to open